In today's video, we're going to talk about coordinate systems. So being able to work in different coordinate systems is a key skill that you should master if you're interested in learning physics, engineering, or math. So in this video, we're first going to review Cartesian coordinates. So we'll review Cartesian coordinates, then we'll introduce polar, cylindrical, and spherical coordinates, which are commonly used in science. And what we're going to do is for each of these coordinate systems, we're going to go through how to find the unit vectors, the differential displacement vector, the surface area element, and the volume element. So let's start with Cartesian coordinates. So in Cartesian coordinates, we have three axes, right? We have the x, the y, and the z axis. And we also have three corresponding unit vectors, ux, uy, and uz. And actually, we can write these unit vectors in the following way. So ux is just 1, 0, 0. Uy is 0, 1, 0. And uz is 0, 0, 1. So the next thing we can ask is, how do I describe something's position in Cartesian coordinates? So as you can see, I've written my position vector r, which is this red arrow. And to know the position vector r, I need to know where I am on the x-axis, so this is this length. I also need to know where I am on the y-axis, which is this length, and I need to know where I am on the z-axis, which is this height. So actually my position vector can just be written as r equals x times ux plus y times uy plus z times uz. So this is the position vector. And actually this definition I've given you is quite general, because in any coordinate system, we can write the position vector this way. Okay, so that's nice. So the next thing we're going to introduce is the differential displacement vector. So the differential displacement vector is a vector that characterizes a tiny translation between two nearby points. So if I have another point here, which is going to be r plus dr, well, my differential displacement vector is just the vector that takes me from r to r plus dr. So I can just write it like this, dr. And actually, to compute dr, all we have to do, so we have our dr there, all we have to do is substitute for r the expression for the position vector, so this one. So let's write it out. So we have d of x times ux plus y times uy plus z times uz. So the next thing I'm going to do is I'm going to distribute this differential to the terms in my sum, right? Because the differential of a sum is the sum of the differentials. So I can just write this as d bracket x times ux plus d bracket y times uy plus d bracket z times uz. So the next thing we need to recall is the product rule for differentials, right? So if I have d of u times v, it's going to be u times dv plus v times du, right? This is the product rule for differentials, and I'm going to apply this to these three guys I have over there. So what's that going to give me? That's going to give me dx times ux plus x times dux, right? And actually, if we look above, the way we've defined the unit vectors is as constants. So actually, ux, uy, and uz don't depend on anything, so their differentials vanish, right? So this becomes 0. And the same thing happens for duy and duz. So actually, I can just write this as dxux plus dyuy plus dzuz. So let's write it neatly in this block. So the differential displacement vector dr is dxux plus dyuy plus dz times uz. Okay, so this is the differential displacement vector. So now we're going to talk about the surface area and the volume elements. So what do these represent? So actually, it's pretty simple. The surface area and the volume elements represent the area or the volume I'm sweeping as I go from r to r plus dr. So let me illustrate this with a drawing. So if I have my vector, let's do this here. So if I have my vector r like this, and here I have a point, so this would be r, this would be r plus dr, and as you can see as I'm going there, so let me draw this out, I am basically spanning this cube, right? I'm spanning this cube, and this length is dx, dy, and this height is dz. Okay? So the volume element is just the volume I'm sweeping as I'm going from r to r plus dr. So all I have to do to find the volume element is to multiply the components of the differential displacement vector, right? Because you can see that the area of this cube, or of this shape, is just going to be dx times dy times dz. So we can write this over there. So dv, right, this is the differential volume element, is dx, dy, dz. So this is just the volume I'm sweeping as I go from r to r plus dr. And also, for example, if I'm only moving along two of the axes, then I don't have a volume that's being swept, I have a surface. So for example, if I'm only moving on the y and z axis, I'm sweeping this red surface, which has an area dx dy. So actually, based on the displacement I'm doing, that there are three choices for the differential surface area element, so ds. So if I'm only moving along the x and y axis, it could be dx dy. If I'm only moving along the x and z axis, it could be dx dz. And if I'm only moving along the z and y axis, ds would be equal to dy times dz. Okay? So this is how you find the unit vectors, the position vector, the differential displacement vector, and the surface area and volume elements in Cartesian coordinates. And actually, in the new coordinate systems we're going to introduce, it's going to be the same method, right? So if you've understood this, then you're ready to move on to the more advanced things. So now we're ready to move on to the next coordinate system, which is going to be polar coordinates. So as you can see, polar coordinates are a 2D coordinate system. So as usual, I have my x and my y axis. But in polar coordinates, what we do is we introduce this distance r and this angle theta. Okay, so r is just the distance from the origin, and theta is the angle made by this red line and the x-axis. Okay, so these are my new coordinates. So the first thing we're going to do is we're going to understand what is the relationship between x and y and r and theta. So what is the relationship between x, y, and r and theta? So how do I go back and forth between these Cartesian coordinates and these polar coordinates? So the first thing I'm going to do is we see that we can draw a right angle triangle here, right? This is a right angle, and if I call this distance from the origin to here x, and this height y, we see that we have a right angle triangle with a hypotenuse of length r, and there's an angle theta over there. So we see that x is just r cosine theta. So x is r cosine theta, and likewise y is just r sine theta. Okay, so this is how we find x and y in terms of r and theta. We also can express r in terms of x and y by using Pythagoras' theorem, right? So r is just x squared plus y squared square rooted. And finally, we see that y over x is equal to the tangent of theta, so theta is the arctangent of y over x. Okay, so this is how we go back and forth between r and theta and x and y. So the next thing we're going to do is the same thing we've done for Cartesian coordinates, is to try and find an expression for the unit polar vectors. So I've drawn them there, so we have this ur vector and this u theta vector. Okay, so how do I find the ur vector? We're going to use a similar method because we can draw another right angle triangle. So this is theta, and the hypotenuse length is 1. Okay, so to go to ur, I have to go this length in the x direction plus this height in the y direction. Okay, and actually we see that this length is just cosine theta, and this height is just sine theta. Okay, so actually my ur is just cosine theta times the x direction plus sine theta times the unit y vector. So ur equals cosine theta ux plus sine theta uy. And we can also do the same thing for the unit theta vector. So I can draw another right angle triangle, and this is my angle theta now, and this again has length 1. Okay, so now we have to go by a distance, by this white distance in the x direction and this height in the y direction. Okay, so what is this distance? This distance is just sine theta. Okay, and this distance is cosine theta. But now we have to be a bit careful because we're going in the opposite direction, right? Because the way we've defined ux is the positive ux points to the right. So this would be minus sine theta ux, right? Because I'm going in the opposite direction. And then cosine theta uy because I'm going upwards. Okay, so my unit vector, unit theta vector, u theta, is going to be minus sine theta ux plus cosine theta uy. And actually we can see from these two expressions that ur and u theta are orthogonal, right? Because if I take the scalar product, we have cosine theta times minus sine theta plus sine theta times cos theta. So their scalar product is 0, so they're orthogonal. And this is a nice thing to check. Okay, so now we're going to find our position vector in polar coordinates, right? So remember, how did we do this for Cartesian coordinates? In Cartesian coordinates, we gave the definition, okay, so I'm going to write it over there, that r is equal to xux plus yuy. So I'm not going to draw z here because we're only in 2 dimensions, so we can say that z is 0. Okay, so we define the position vector as xux plus yuy. So all we have to do to find the position vector in polar coordinates is to plug in for x and y the expressions we found in terms of r and theta. So we replace x by r cosine theta and y by r sine theta. So what does that give me? That gives me r cosine theta ux plus r sine theta uy. So what I can do now is factor this r outside, which is going to give me r times cosine theta ux plus sine theta uy. And actually you may notice that the term in the brackets is just the unit r vector we defined previously. So this is our ur, right? See if, let me just show it to you again. Ur is cosine theta ux plus sine theta uy. Okay, so what does that tell us? That tells us that the position r is just the distance r times ur, the unit vector. And you see this makes sense because if I know, so if we look at this graph, if I know what my distance is from the origin and I know in what direction I'm pointing, then I know my particle's position in polar coordinates. So let's write this down. So r is just r times ur. So that's a nice and neat expression. Next thing we're going to do now is, as we did for Cartesian coordinates, is find the differential displacement vector. So we're going to do exactly the same thing that we did before. Okay, so the differential displacement vector, dr, is just d of rur, right? It's just a differential of the position vector. So I'm going to apply the product rule again. Okay, so what does that give me? That gives me dr ur plus r dur. Okay, but now something interesting is going to happen because remember, in Cartesian coordinates, these dux, duy, and duz vanished because they didn't depend on anything. But we see that the way the unit vectors are written down, ur and u theta, they both depend on the angle theta. So the differential is not equal to 0. So we have to find dur, so the differential of ur. So maybe now would be a good time to quickly review multivariable calculus. So if we have a function f of n variables, so x1, x2, all the way up to xn, well then the differential of this function, df, is df, so partial f by partial x1, dx1, plus partial f by partial x2, dx2, all the way up to xn. So what we can do is we can write dur in terms of these partial derivatives with respect to r and theta. So we can write that dur is equal to dur by dr plus partial ur by partial theta, d theta. So So let's look again at our expressions for the unit r vector that I have over there, right? So ur equals cosine theta ux plus sine theta uy. So actually ur does not depend on r. So this is nice because it simplifies things for us, right? We don't have to calculate this, it becomes 0. Okay, so all that we have to calculate is partial by partial theta of cosine theta ux plus sine theta uy. Okay, so let's differentiate these terms. So that's equal to, so differential of cosine theta with respect to theta is minus sine theta. So minus sine theta. Ux is just a constant, so I'm going to keep it there. And then derivative of sine theta with respect to theta is cosine theta. So plus cosine theta uy. Okay, so actually we notice another interesting thing happens is that this is just the unit theta vector we defined. Right, let me show it to you again. Right, this is minus sine theta ux plus cosine theta uy. So it's the unit theta vector. So what does this tell us? This tells us that dur is just d theta u theta. Right, so remember dur is partial ur by partial theta d theta. Okay, so now let's write our differential displacement vector down. So our differential displacement vector dr is equal to dr times ur plus r d theta u theta, right? Because we said it was dr ur plus r dur, and dur is d theta u theta. So now we have our differential displacement vector in polar coordinates, and now we can compute the surface area element. So there's no volume anymore because we're only in 2D. And remember I said that the surface area element is just the area that I'm sweeping as I go from r to r plus dr. And so the way to find the surface area element is just to multiply the different components of dr. So this gives us ds equals r dr d theta. Okay? So this is how you find the coordinates, the unit vectors, the position vector, the differential displacement, and the surface area element in polar coordinates. And so the next coordinate we're going to see now is the cylindrical coordinate system, and actually it's going to be really easy because it's very similar to the polar coordinates. So this is the setup for cylindrical coordinates, and as I just said, it's very similar to polar coordinates, right? Because you see, again, I have this blue line r, which is exactly the same r than the one we had in polar coordinates. I also have this angle theta, which is again exactly the same, but the only difference is that now we're in 3D, so we have this height z. So actually, if we look at the expression for our coordinates, x is just equal to r cosine theta, which is the same for polar coordinates, y is r sine theta, and z is just z, which is the coordinate, the Cartesian coordinate z, so it's the height. And again, we have r equals root x squared plus y squared, and y is the theta is the arctangent of y over x. Okay, so to speed things up, I've just rewritten the unit vectors because they're going to be the same than the ones we've seen previously, right? So ur is cosine theta ux plus sine theta uy, u theta is minus sine theta ux plus cosine theta uy, and uz is just 0, 0, 1, right? Uz is the same Cartesian unit vector. Okay, so let's talk about the position vector. So if you can see, right, if I want to describe this red vector r, I have to move by a distance r in the ur direction, right? This blue line is the ur direction, and then I have to move by a height z in the z direction. So it becomes really simple because the position vector in cylindrical coordinates is r equals rur plus z uz. And actually, if you think about it, it does make a lot of sense because rur just tells me what my position is in the xy plane, and zuz just tells me what my height is. So this is nice and simple. So now what we can do is we can compute the differential displacement vector. Okay, so the differential displacement vector is always going to be the same thing. dr is just going to be d of rur plus zuz. So I'm going to do exactly what I've been doing since the beginning. I'm going to distribute the differential to the terms in the sum and then apply the product rule. So that gives me d r ur plus r dur plus dz uz. And then we're going to have a z duz, but remember uz is just constant, so its differential vanishes. And actually this r dur, we've already calculated it before, it's just r d theta u theta. It's the same ur than the one we had in polar coordinates. So we can just write our differential displacement vector neatly. So dr is drur plus r d theta u theta plus dz uz. So that we have all of this, we can write down the volume and surface area element in cylindrical coordinates. So remember, the volume and the surface area element is just the volume or the surface area I'm sweeping as I go from r to r plus dr. So all you need to do is multiply the components of the differential displacement vector. So my dv is going to be r dr d theta dz. And then for ds, we have three choices. Okay, so if I'm not moving along the r direction, it would be r d theta dz. If I'm not moving along the z direction, it would be r dr d theta. And if I'm not moving along the theta direction, it would be just dr dz. So this is how you find the unit vectors, the position vector, the differential displacement, and the volume and surface area elements in cylindrical coordinates. So now we're ready to move on to the final coordinate system, which is going to be spherical coordinates. So I've drawn the little setup over there. And so actually spherical coordinates is probably the trickiest coordinate system to deal with because the math is a bit more involved, but we'll get through it together. So as usual, I have my x, y, and my z axis, so x, y, and z. And so in spherical coordinates, what we do is we introduce this distance r from the origin, right, which is the length of this red vector. We also have this angle phi, and actually the angle phi is exactly the same than the angle theta from polar and cylindrical coordinates. The reason why I'm calling it phi is because I want to follow the conventions that most textbooks use. Okay, so phi is the exact same thing than the angle in polar and cylindrical coordinates. And then we have this angle theta between the r vector and the z-axis. Okay, so another thing I'm going to do is I'm going to introduce this blue length, this one, rho, and I'm going to call it rho, and actually it's the same than the r distance from polar and cylindrical coordinates. So it's going to be very useful for our later derivation, so we can just write down that x equals rho cosine phi, y equals rho sine phi, and then we have our unit vector u rho, which is the same than the ur vector. Okay, so what we're going to do now, which is what we've been doing since the start, is to figure out how do we go from Cartesian, so how do I find the expressions for x, y, and z in terms of r, theta, and phi, and vice versa, right? So how do I go between my Cartesian coordinates and my spherical coordinates, right? So the first thing that we can notice is that we have a right angle triangle, right? So this one, and this angle over there is actually theta, right? So we have a right angle triangle with a hypotenuse of length r. One of the sides has length rho, and there's an angle theta over there. So maybe what we could do is try to express rho in terms of r, right? And we see that actually rho is equal to r sine theta, right? It's pretty clear from this drawing over there. So actually this makes it very easy to get the expressions for x, y, and z in terms of r, theta, and phi, because all I have to do is replace rho by r sine theta. Okay, so let's write it down. So x equals r sine theta cosine phi, y equals r sine theta sine phi. Okay, and then I have back to this right angle triangle, we see that there's a height z and an angle theta over there. So that tells us that z is equal to r cosine theta. Okay, so this is pretty nice and simple. So the next thing we can do now is express r, theta, and phi in terms of x, y, and z. So I've already written down the expression for phi because it's the same than for theta in polar and cylindrical coordinates. But what we can do is express r, so the distance r, right? So we see that we have a right angle triangle of height z and of side length rho, so we can use Pythagoras, right? So if we use Pythagoras, we get that r squared equals rho squared plus z squared. But remember, rho squared is just x squared plus y squared. Okay, so this gives us the expression for r. So r equals x squared plus y squared plus z squared square rooted. Okay, now for the angle theta, since we just said that z was equal to r cosine theta, that means what? That means that cosine theta equals z over r. Okay, so theta is the r cosine of z over r. So theta equals r cosine z over r. Okay, and actually r is just root x squared plus y squared plus z squared, but I'm not going to write it there because it would take too much space. All right, so this is how we go back and forth between our Cartesian and our spherical coordinates. So the next thing to do on the list is to find the expression for our unit vectors. Okay, so we already have the u phi vector because it's the exact same thing than the u theta vector from cylindrical and polar coordinates. Okay, so we need to find our ur vectors. Okay, so actually to find the ur vector, we have to use again this rho and our u rho vector. Okay, so in green I've drawn my unit spherical vectors. So what we're going to do is we're going to draw our u rho vector. So our u rho vector would go something like this. Okay, so this would be u rho, right? So I see that I have this right angle triangle. I have an angle theta over there, and the hypotenuse is length 1, right? So what I want to do to get my ur vector is I want to go this length in the rho direction plus this length in the z direction, right? This is how we find the unit r vector. Okay, so how do I find this length? Well, we can see that this length of this white line I'm drawing over the green arrow is just sine theta, right? And the length of this one is just cosine theta. Okay, so I'm going sine theta in the rho direction plus cosine theta in the z direction. So let's write this down. So ur equals sine theta u rho, but remember u rho is cosine phi ux plus sine phi uy. So sine theta cosine phi ux plus sine theta sine phi uy, and then we're going cosine theta in the z direction. So cosine theta uz. Okay, this is my unit r vector in spherical coordinates. Okay, so now how do we find the unit theta vector? So the trick to finding the unit theta vector is to notice that this angle over there is also theta. So maybe let's do a drawing to make this a bit more clear. Okay, so if this is my z-axis, okay, if this is my ur vector, then my u theta vector would be normal, so orthogonal to it, so u theta, and then my u rho vector would be in between, right? This would be my u rho. So what did we say? We said that there was a right angle over there. This was an angle theta. So what does that mean? That means that this one is pi over 2 minus theta, right? Because the sum of the angles in a triangle is always 180 degrees, or pi radians. But what do we know? We know that ur and u theta have to be normal to each other. So that means that this one is a right angle. So actually, the only way this one is a right angle is if this is theta, right? So actually we have another right angle triangle over there. Okay? So now to go, right, to express my u theta vector in terms of ux, uy, and uz, we have to go this length in the u rho direction, and then we have to go downward. So we're going this length in the minus uz direction, right? Because remember we said uz was 0, 0, 1. So uz points upwards. If I'm going downwards, it becomes minus uz. Okay? So actually this length, right, the length of this green line I'm redrawing is going to be cosine theta. So this is cosine theta. And this one is going to be sine theta. But remember, I'm going downward, so in terms of vectors, this would be minus sine theta uz. Right? So now we can write down the expression for our unit theta vector. Okay, so u theta, what did we say? We said it was cosine theta times u rho. So cosine theta cosine phi ux plus cosine theta sine phi uy minus sine theta uz. Okay, so this is how we find the unit spherical vectors in spherical coordinates. So again, as we've been doing since the beginning, the next step is to find how to write the position vector. Okay, so how do we write the position vector in spherical coordinates? So the method's always going to be the same, right? The position vector r is always given by x ux plus y uy plus z uz. Okay, this is my position vector in any coordinate system. So all we need to do to find the expression for the position vector in spherical coordinates is we have to substitute for x, y, and z the expressions that we found over here. So we're going to have to use this, this, and this one. Okay, so let's write all of this down. So it's equal to cosine phi sine theta ux plus sine phi sine theta uy, sorry, there should be an r over there, plus cosine theta uz. Okay, so this is my position vector in spherical coordinates. So what I'm going to do is I'm going to pull out a factor of r, so I can write this as r cosine phi sine theta ux plus sine phi sine theta uy plus cosine theta uz. And so you might notice that actually what I have in my brackets, this one, this term, is just my unit r vector in spherical coordinates, right? So let me show you my unit r vector that we found. All right, we said that ur was sine theta cosine phi sine phi uy plus cosine theta uz. So actually my position vector in spherical coordinates r is just r times ur. Okay, so that's again a nice and compact expression. All right, so the next thing we have to do is we have to compute the differential displacement vector. Okay, so we have to compute the differential displacement vector, and remember, we're going to do the same thing than what we've been doing since the start, is to say that the differential displacement vector dr is just the differential of the position vector. So in our case, it's r times ur. So what I'm going to do is I'm going to use the product rule for differentials. Okay, so that's going to give me dr ur plus r times dur. Okay, but now we want to be a bit careful because, right, something interesting is going to happen. You see that my ur, right, this one, depends on both theta and phi. So we have to do the same thing than what we did for polar coordinates, right, is to compute the differential of ur, so dur. Okay, right, so we see that ur has no dependence on r, so we can just write that dur is equal to partial ur by partial theta d theta plus partial ur by partial phi d phi. Okay, so let's compute these terms. Okay, so let's do dur by d theta. That's what partial by partial theta of sine theta cosine phi ux plus sine theta sine phi uy plus cosine theta uz. Right? So I have to take the partial derivative of this expression with respect to theta. Right? So what I'm not going to do is touch these phi terms, right? Because these phi terms are treated as constants. Okay, so derivative of sine theta is cosine theta. So that gives me cosine theta cosine phi ux plus cosine theta sine phi uy minus sine theta uz. Okay, so you might notice that actually this, what I have, is just my unit theta vector. Yeah, let me show this to you again so it's clear. Right, my unit theta vector is actually this one, cosine theta cosine phi ux plus cosine theta sine phi uy minus sine theta uz. Right, so this is exactly what we have. Okay, so dur by d theta is just my unit theta vector. So let's move on to the next partial derivative. So dur by d phi, so what is that equal to? That's equal to partial by partial phi of the expression of this expression, right? So instead of just writing it out again, we can directly compute it. All right, so derivative of cosine phi is going to be minus sine phi. So remember, I'm taking my partial derivative with respect to phi, so I don't touch anything that has a theta in there. Okay, so what's that going to be? That's going to be minus sine theta sine phi ux plus sine theta cosine phi uy, and then there's no phi in this term, so this becomes 0. So actually what I can do is I can pull out a factor of sine theta from this expression. So that's going to give me sine theta times minus sine phi ux plus cosine phi uy. And actually what I have in my brackets is just my unit phi vector. Right? Let me just show it to you again. The unit phi vector, the way we've computed it is we said it was minus sine phi ux plus cosine phi uy. So actually the derivative, the partial derivative of my unit r vector with respect to phi is just my unit phi vector times sine theta. Okay, so now let's try and put all of this together. Let's put all of this together, right? So we said that dr, the differential displacement vector, was equal to dr times ur plus r dur. Okay, and so our dur is just dur by d theta, right? So that's going to be equal to d theta u theta plus sine theta d phi u phi. Yeah, this is my dur. Okay, so what I'm going to do now is I'm going to write out the differential displacement neatly over there. Okay, so dr is dr times ur plus r dur, so we have r d theta u theta plus r sine theta d phi u phi. Okay, so this is my differential displacement vector in spherical coordinates. So you see the expression is a bit more tricky than in the other coordinate systems we've seen. Right, so the final thing we have to do is to find the surface area and the volume element. But again, as I've been saying since the beginning, the surface area or the volume element just represent the area or the volume that you sweep as you go from r to r plus dr. So all you have to do is multiply out the components of the differential displacement vector. Okay, so we can just write that dv is, so I have r d theta times r sine theta d phi times dr, so r squared sine theta dr d theta d phi. And then if I'm only moving along two of the axes, so if I'm not moving along one of the directions, we have surface area elements, right? So if I'm not moving along the r direction, right, my surface area element would be r squared sine theta d theta d phi. If I'm not moving along the theta direction, it would be r sine theta d phi dr. And if I'm not moving along the phi direction, Well, my surface area element would just be r dr d theta. Okay? So this is how you find the coordinates, the unit vectors, the position vector, the differential displacement vector, and the surface area and volume elements in spherical coordinates. So thank you very much for watching this video, and I hope you enjoyed it.